Good morning, students. It's Misty. Today, I'm here to walk you through your objectives for Monday, the 23rd of March. And by now, you should have received the weekly e-learning planner. This was posted in Google Classroom. So if you scroll down to our learning activities today, you'll notice there are 4 of them to complete, 3 to complete in class, and 1 homework, which is due on Wednesday at 8. So tasks today include checking out a graph titled Global Monthly Means for Greenhouse Gases. You don't need to spend more than 10 minutes on this. I'm just asking you to quickly comment on the classroom. The next is to watch a video clip, which you can click right here. And then finally, to complete your Keeling curve formative, thank you to those of you who have already started on that. Nice job. And I'll just walk you through the slides for today. We're still in our carbon cycling and climate change unit, and today your learning targets is to determine patterns in monthly mean concentrations for various greenhouse gases and the type of function that models the data. And you can see here that there's a little bit of computational thinking involved here. Our anchor standard is computational thinking, in addition to arguing from evidence. So you'll notice that the video today is bringing a little bit of math into this class. And for the first 5, I had you tape some graphs into your notebook. If you don't have them, you can just click on that link in our agenda. And note 3 things that you notice about the graphs and 3 things that you wonder. Share out in our question post in Google Classroom. You can take a moment to do that now. Once you're done with the first 5, I just wanted to point out some of these graphs. These are one way of visualizing data, and hopefully they look familiar to you. We've seen a similar graph for carbon dioxide, atmospheric carbon dioxide concentrations from Mauna Loa. And as we think about visualizing and understanding these data, this invites computational thinking. And it is an approach to solving problems that requires us to think recursively, to model relevant aspects, and use abstraction and decomposition in tackling complex problems. So what does that mean? That's kind of it's a lengthy definition. What that really means for us is that computational thinking is simply an opportunity to guide data practices in science. So data practices might include things like collecting data, manipulating data, analyzing data, finding the best way to visualize the data. And the practices we're using for this unit is pattern recognition, which we've already done, abstraction, which we've also thought about and modeled, and algorithm building, which I'm introducing this week. We touched on it a little bit last week. So when you look at a graph like this was the monthly mean CO2 concentrations at Mauna Loa. You've seen this now for a couple weeks, and we looked at pattern recognition in here. This is identifying, clustering, and modularizing steps, parts, or correlations that repeat and can be repeated. So when you look at this graph, you might ask yourself, well, what are the patterns we can see in the graph? And we've talked about the seasonal pattern, right? How do visualizations change as we add more data? We've made some predictions or thought about what this might look like in the future. Do the data look random or are they regular? We've agreed as a class these data do follow a regular pattern. Are there increasing and decreasing patterns? Again, a lot of you recognize this right from the start. There's an increasing pattern to these data. And what shape are the data? And many of us said, well, I think it's a linear fit. And some other people were like, well, maybe it's not linear. Maybe there's a different kind of shape that we can describe with these data. So that's pattern recognition. Hopefully this feels familiar. You've already done this data practice as it pertains to computational thinking.